All right, we ready for some more math today? Hopefully you did the lesson part 1 that was for yesterday's digital day. If you didn't, you're going to be a little lost today, so you really have to do that lesson, otherwise you're going to have no idea what's going on today. So, moving into today, we've got all that log base 2 information, and because we converted the colors of the DNA microarray into numbers, and now we're going to be taking those numbers for Mike and comparing them to other patients that have had successful chemotherapy treatments and picking a medication for Mike. So Mike's DNA microarray analysis is back from the lab and has been converted into base 2 logarithm form. You're welcome. Your job is to use the base 2 logarithms to calculate the Pearson correlation coefficient. Use the Pearson correlation coefficient to statistically compare Mike's gene expression profile to the gene expression profiles of 4 patients, each whose cancers were known to respond to a particular chemotherapy medication. The correlation coefficient will indicate the relationship between each gene expression profile and help you advise Mike's oncologist as to which medication Mike's cancer would likely respond to the best. So, here's the data we're going to be working with today. So you've got our guy Mike Smith here, and we don't know which chemo works for him. And then we've got information for 6 of his genes, and we've got the log base 2 number of the ratio of red to green of those colors. So like, for example, 0 means that it's not turned on in either the healthy cells or the cancer cells. And you can see that that's for all these patients as well here. So we know that gene 1 has nothing to do with the cancer for Mike or these other patients. But then you've got, the rest of these numbers here for the other genes for Mike here, which we know that a positive number, hopefully you remember from yesterday's video, means that it's upregulated in the cancer cells, okay? Patient 2 also has all these positive numbers, upregulated genes in the cancer, all these positive numbers upregulated in the cancer. Patient 3, these ones are all positive. This one had no difference between the two, but upregulated the cancer for the rest. And then patient 4 has a whole bunch of negative numbers, meaning that they were downregulated in his cancer. So you can see that even though it might be the same type of cancer, that they can all have different gene expressions. And so our job today is to figure out which set of numbers between patient 1, 2, 3, and 4 are most similar to Mike's set of numbers. Okay, and just by looking at it, that's really hard to figure out, like, which set of numbers is most similar to another set of numbers. So we're going to go through a formula. It's a little hefty, I will warn you up front here, but I know we can do it. So it's called the Pearson correlation coefficient formula, how correlated or how related 2 sets of numbers are. So it's going to be using this variable, or the value R, the letter R, to be able to represent the Pearson correlation coefficient. That's what we're going to be solving for R today. And it's just going to show us how similar 2 sets of values are to one another. Now you're looking at this formula and being like, oh my goodness, but we're going to break it down. So you definitely are going to need some scratch paper, a calculator today. If you want to print out these notes, I've got them posted in Schoology, and you can print them out, and it kind of takes you like through a worksheet step by step. But you can definitely just also write it out in your lab notebook or a scratch piece of paper. So yeah, make sure you get those things here. You guys can pause the video if everybody needs to get stuff, unless you already have it, hopefully. Otherwise, go ahead and grab it real quick. And moving forward. So whenever we're tackling a formula with so many functions in it, it's best to break the formula down into its different smaller parts. We're going to break down the formula into its different functions and complete the math step by step all together here. And for this instance, we're going to just compare Mike to patient 1 first. So you're going to have to compare Mike to each of the different patients, okay? So separately. So we're going to compare Mike to patient 1, then Mike to patient 2, then Mike to patient 3, then Mike to patient 4. And then you're going to see which one is the most similar to Mike. So, step 1. So I'm always going to have our formula up here in the top right corner. We're going to break down this formula and go through it step by step. So, the first thing that we're going to do is we're going to solve for this X with the line over it and the Y with the line over it. And that is our means or averages for both arrays. An array is just a set of numbers. So Mike's array and patient 1's array are right down here. Mike's right here, patient 1 right here, and we want to solve for the average, right? So hopefully we know an average formula, but they're both right here for X and for Y. It's the same, just X and Y. But you're just going to find the average of the numbers in that set. So you've got, for Mike, it would be 0 plus 3 plus 3.58 plus 4 plus 3.58 plus 3 divided by, you got n here, which is the number of numbers that you have in your set, which we have 6 genes that we're looking at, 6 numbers, so divided by 6. When you do it all up together, you add them all up and divide by 6, you should get 2.86. And then same thing for Y's is going to be patient 1. So Mike will be X for all of these, and then Y will always be whatever patient we're comparing to. So patient 1 is our Y's. So again, this was our X equals, so our Y mean equals 0 plus 1.58 plus 2 plus 2.8 plus 1.58 plus 1 all over 6 as well. And that will get you 1.493. So now we can plug in 2.86 into our mean X over at the top here. 2.86 goes right there, and 1.493 goes right there. So just make sure you label and circle these numbers on your work so that when you need to plug it in, we can go back to it. Then the second step, we have to calculate the deviance. Or we've got the xi minus the mean of x and yi over the mean of y. So the deviance is how far away from the mean is each individual value, right? So in order to do that, you're going to have to take the first number here, 0, subtract it from the mean, which we have back here. Our mean was 2.86. So 0 minus 2.86. Then the next number, 3 minus 2.86. 3.58 minus 2.86. 4 minus 2.86. And 3.58 minus 2.86. 3 minus 2.86. And these are all going to equal your xi minus the mean of x. So you're going to just do the simple math for that. So you've got negative 2.86, 0.14, 0.72, 1.14, 0.72, 0.14. That's all our deviances for Mike. Then you do the same thing for patient 1 here. You're going to take their first value, which is 0, and you're going to subtract by the mean for patient 1, which if we go back was 1.493. So minus 1.493. Second number, 1.58 minus 1.493. 2 minus 1.493. 2.8 minus 1.493. So we're just figuring out for each value how far away it is from the mean. All right, so if you do the math for that, minus 1.493, 0.087, 0.507, 1.307, 0.087, and negative 0.493. So again, these are what your yi minus y is representing. Okay, so that's step 2. You've got this whole set of values now for each Mike and patient 1. And you're going to have to multiply every deviance to the other patient's deviance. So all of Mike's deviances need to be multiplied by patient 1's deviances. So you're going to take this first one here and multiply it by this one here. So you've got negative 2.86 multiplied by negative 1.493. Okay, and going back to the formula up here, you've got the 2 parentheses. We're working our way out now. We've solved what's in the parentheses. Now we're going to do the parentheses together here. So that's why we're multiplying them together. Hopefully you see that in the formula, the numerator there. 0.14 times 0.087, got it right here, times right here. So just keeping everything lined up. So doing your work neatly is going to be really, really helpful in this case. 0.72 times 0.507, those two numbers there. 1.14 times 1.307, over there. 0.72 times 0.087, and 0.14 times negative 0.493. Okay, so you solve the math for each of those. So we're going to have, I'm going to put it over here since we don't have room on the side there. So the first one, negative 2.86 times negative 0.1493 gives you 4.271. Then you've got 0.012 for this next answer here. Next one down, 0.365, 1.490. Then you got 0.062 for the fifth one down, and then the last one is negative 0.069. Okay, so you've got the set of 6 numbers here as you're multiplying of the 2 deviances between Mike and patient 1. And then the next part in our formula up here at the top, we've multiplied the 2 deviances to one another, and then we've got this funny looking E, which if you remember, or if you've learned in math, hopefully, that means the sum. So we're going to take all of these numbers in our set here and do what? We're going to calculate the sum, add them together. So you're going to take all those numbers, add them together, and when you add them all together, you should get 6.1308. Okay? So now we've figured out the numerator. This is our numerator. This is really important. Definitely circle that, label it as your numerator so you don't have to find this number when we get to the point where you take the numerator and divide it by the denominator. Okay? Hopefully you're hanging with me. I know it's a lot, but you can do it. It's really just multiplying, dividing, subtracting, some adding, pretty basic math. Just looks a lot more fancy and complicated in this formula. All right, now we're going to move down to the denominator down here. So we're going to work through our denominator. You're going to take your arrays, which we already solved the arrays, so that's why you definitely want to keep your work organized and neat here. This was our deviances for each of the arrays, so how far each number was away from the mean, and you're going to square each of them. Okay, so you're just going to take each of these numbers and square them. So when you square them, you're going to get 8.180, 0.020, 0.518, 1.3, 0.518, and 0.02. And for your y's over here that are squared, you're going to get 2.23, 0.008, 0.257, 1.707, 0.008, and 0.243. Right, so that's your square for each of them, because you can see here in the bottom in the denominator of the formula that each of those deviances were squared. See right here, squared and squared. Okay. Now the next step you should be able to see is going to be that you're going to have to sum up each of these squares. So, showing you here, you add up all those numbers from this last slide. So we had all these numbers here, add them all up together. All these numbers here, add it all up together. And when you do that, you get for the X, for Mike, 10.555, and for the Y, for patient 1, 4.452. Then if you look at our formula, you've got your sum and your sum. You're going to be multiplying those together. So 10.55 is going to get multiplied by 4.452. Going to give you 46.997 when you multiply those together. Last step then, in our order of operations, is our square root in that formula. So you're going to take the square root of 4.46.997. When you take that square root, you are going to get 6.855 for your square root. And then you're going to take your numerator and your denominator and put them together and figure out the number. So if you remember, your numerator should have been, if you had labeled it nicely in your notes, was 6.1308. So that's our numerator. Denominator 6.855, which took that square root. And that means our Pearson correlation coefficient you should get equals 0.894. Okay, and you have to do this for, that's how, that's the correlation coefficient between Mike and patient 1. And then so we have to do Mike and patient 2, Mike and patient 3, Mike and patient 4. And you're probably like, oh my gosh, has Mrs. Pelletier lost her mind? Because that is way too much math, not doing it, overdone, no way. But as you might have seen on accident, so to the next slide, there has to be an easier way, and guess what? There is, because like I said, computers are smarter than humans, or at least not smarter necessarily, but can do things a lot faster than we can by working that all out by hand, as well as we can make lots of mistakes along the way. So you can use Google Sheets to do all of this for you. So what you're going to do is you're going to end up opening up a new Google Sheet. You're going to put all of the DNA microarray results into the cells in Google Sheets. So you just copy down this table here. And then you're going to create a row underneath for the correlation coefficient. You don't need one for Mike because we're comparing Mike to each of the patients. So you'll just put it underneath each patient, how similar Mike is to each of those patients. So what you'll do, and I'll probably create a separate video showing you exactly in Google Sheets how to do this, but the basics are in the correlation coefficient box underneath patient 1, which is this box right here, you would just type an equal sign, which is going to bring up your formula generator, and you type in Pearson. It's actually already loaded into Google Sheets for you, so you don't have to type in this whole formula. You could type in the whole formula and use it that way, but they've created a shortcut for you in Google Sheets. You just type in Pearson, and then you select your first set of data, your first array. So you just click and highlight over all of Mike Smith's numbers, which will be like right here. And then you hit comma, and then you highlight and select all over patient 1's numbers, and then just hit enter. And look, that's the number that we calculated together, 0.895 or 4 or whatever. So that's the number that we calculated together. And you're probably like, what the heck? Why'd you make us do all this? Because I really want you to understand how to do the math behind a formula so that you understand what the formula is actually doing for you. Okay? And so then you can do this for patient 2, 3, and 4. Since we already did patient 1, you don't have to do patient 1 necessarily. But then you would just, in the box under patient 2, hit your equal sign, type in Pearson, and then you would highlight Mike's set of numbers, comma, and then patient 2 set of numbers, hit enter, and it'll give you the correlation coefficient for patient 2 and Mike. And you can see then that number. Now, we haven't talked about what that correlation coefficient actually means. So again, this is something that you definitely want to write down in your notes. Our correlation coefficient, when it's positive, that means that the gene expression profiles behave similarly. And that's what we're looking for in this case, right? We want to see which set of DNA microarray results from these 4 patients is most similar to Mike. So we want to find a positive number, and the larger the correlation coefficient, so the more positive the number is, which they're only going to go up to 1 is going to be the highest, the stronger the relationship. If we've got a negative number, those ones are people that we can rule out completely because their DNA profile behaves in a completely opposite way than Mike's would. So the further away from 0 or the more negative it is, the more opposite the relationship. So if it's really, really negative, it's going to be really, really opposite from Mike's. If the correlation coefficient is 1, the profiles are completely identical. That would be like the ideal situation, really unlikely, but that would be perfect. And then 0 means that they just behave in a completely unrelated manner to one another, have no correlation whatsoever to one another. We wouldn't want a 0 either. Okay, so we're looking for the highest positive number that we can. So your job today is to figure out the correlation coefficients between Mike and then each of the patients we haven't done today, 2, 3, and 4. If you want to work out the work all on your own by yourself in your notebook by hand, more power to you. I would love if you wanted to do that. Get you a lot of practice with your math skills. But I also understand if you're like, I got things to do, lady, don't make me do all that. You can just use Google Sheets and make it a lot faster. Okay, and then you're going to go into Google Schoology and open up 3.5 Part 2 Check for Understanding, where I ask you which chemotherapy drug you're going to recommend to Mike's oncologist to hopefully help cure his cancer. Remember, you're looking for the patient that has the most strong relationship between Mike and the patient. You'll choose that same drug that worked for that patient will hopefully also work for Mike. And then just make sure you do that before you leave class today, right? You're not just hopping off right now. I want you to work on this while you still have your sub, either Mrs. Faith or Mr. Freiberger, there to help and answer any questions that you might have. And then once you're all done, let them know, and then you can sign off, okay? This is so cool because, like I just said, like before in yesterday's video, this is showing you that math can actually help save people's lives. So hopefully this gives you give a little credit to math, even if you hate it, that it does have the power to save people's lives. And in this case, you're going to use it to save Mike's life, hopefully. And I think that is all. You've got a quiz coming up here, so make sure you get to that study guide. You will not need to memorize this formula or anything, but you definitely want to know how to do this for your tests or your quiz as well this week. So have a great day. See y'all soon.